Welcome to the course Advanced Reaction Engineering. So, in this course we are discussing non-ideal reactors. So, here we will discuss two parameter models. So, modeling of real reactors with combinations of ideal reactors. So, in the two parameter models already we have discussed by considering say model systems. So, that was compared with the real reactors. Here this is our real systems and this is the model system. So, by considering these reactions we have developed some equations. Okay. So, these equations we have developed or we have discussed in our last class. So, how to find out the concentrations at this exit of the reactors from the model systems. If we pass a reactions or reactions considering C naught is known for a reactions, and for these reactions rate constant, that is reaction rate constant is knowns. So, if these two parameters are knowns, so and volume tau is also known, volume by volumetric flow rate is known. So, then if we substitute these are the components in these equations, so then Ca, that is the exit concentrations, we can easily predict, but for easily we can find out this. Okay. And from there x equals to Ca naught minus Ca by Ca naught. So, conversions, what would be the conversions we can find out, but before that we need two component, that is the alpha and beta, these are the components we need. So, this is the alpha is the system volume by volume, actual volumes of the reactors, and beta is the volumetric flow rates. So, these are the two components you have to find out. So, once we know Vs and Vb, so this Vs and Vb we have to know, means system volumes and bypass volumetric flow rates if you are able to know, then alpha beta value we can find out and we can substitute in equation 4, then conversions easily we can predict using our two parameter models. Okay. So, today we will discuss about the model system treasure test, means treasure test why it is important. So, you can see it. So, that would be used to solve our model systems. So, here this is the model systems, here we are using treasure. So, here CT0, that is the treasures only passings. Okay, treasures we are passing from here instead of reactions. So, there would be no reaction. In earlier case it going to be that reactions means reactant A was passing through here, through the inlet of the reaction system. So, therefore, we have developed this equation. So, now once treasure is passing through this our model system, so from here similarly treasures also will pass through this and some treasures will pass through this, and then it would come here and it would mixed up at this junction 2, and then outlet treasure concentrations we can get here, and this is the dead volumes. I said that dead volumes equals to 1 minus alpha into V, and Vs system volume equals to alpha into V, and bypass volumetric flow rate that equals to beta into V0, and system volume, that system volumetric flow rate equals to 1 minus beta into V naught, and alpha and beta that we have expressed or we have explained. So, now if there is continuous treasure input is there. So, here we are not doing the pulse input, here step input we are doing, step input means here continuously a particular concentration of the treasures will pass through these reactors. Okay. So, positive step input is there, treasure. So, now this is if we non-reacting treasures and if we do the balance. So, in the system, so input minus output equals to accumulation, since there is no reaction. So, therefore, that part we cannot consider. So, only Vs into CT0, Vs into CT0 minus this out equals to Vs into CTS. Okay. So, this is input, this is output, and this is accumulations Vs into CTS by dt. So, this is the material balance of this particular systems or reactors. So, here this is the in, this is out. Okay. This is the Vs volumetric flow rate, here is also Vs volumetric flow rate, but here concentration is Ct0, and here after some means when the tracer is passing through these reactors. So, some due to the non-aerated nature, so there would be some changes. So, the tracer concentration would be Cts after passing through the reactor. So, therefore, this is the output, this is input, and this is accumulations part Vs dt dCts by dt. Okay. So, now equations 5 we have, and since there is a tracer test, but step input is there. So, the condition for positive step input that we have discussed in our last class also, in before that also, when t less than 0 Ct equals to 0 and when t greater than equals to 0. So, then Ct equals to Ct0, okay, Ct equals to Ct0. So, this is the boundary condition or conditions of step input, positive step input. So, now at junction 2, so if we do the material balance at junction 2, so then we can get Ct equals to Ct into V0. Actually at junctions, if we do the material balance, it would come Ct into V0 equals to Ct0 into Vb plus Cts into Vs, this would come. So, this is at junction 2 at doing the material balance. So, then equation 6 in terms of Ct left hand side and rest right hand side is this. So, now integrating equation 5 and substituting in terms of alpha and beta value. So, equations 5, that is the first order differential equations. So, that equations we have to integrate, and then we have to substitute alpha and beta. Alpha and beta, what alpha and beta, that we know, that is in terms of volume and volumetric flow rates, that is the ratio just. So, that you have to substitute, then from equation 5 we can get this. Okay. So, equation 5 means from where we are getting, this is the material balance inside at this particular point, and equation 6 that we are getting from junction 2. So, now equation 5 we are integrating, since that was first order differential equations, we rearranging this, and after integrating and substitutions of the value of alpha and beta, we simplify these equations 5 into, we can express into as a 7. Okay. So, this is the equation 5. So, equation 5 we are changing in terms of alpha beta after integrations, then we can get Cts is this. Now, Cts by Ct naught is right hand side in terms of alpha beta t and tau. This Ct we want to substitute in equation 6. Why we want to substitute here? Ct is not is known, except Cts, the concentrations that is coming out from the reactor, that is unknown. So, due to the non-ideality or residence times distributions, so Ct concentration should be different. So, this Ct we are substituting here. So, then this equation 6 would be converted in terms of alpha beta and Ct naught, that is known concentration that you are passing continuously, that step input of the tracers. Okay. So, once combining equation 6 and 7, we can get the effluent concentration of the tracer, that is Ct by C naught equals to 1 minus beta exponential minus 1 minus beta by alpha t by tau. So, equations 8 we can get. So, once we rearrange this equations 8, once we rearrange the equations 8, means this equation and 9 equation both are same, just we are rearranging. So, we are rearranging, after rearranging, so we can get equation 9. After rearranging the equations, we can get equation 9, both are same. So, equations 8 we are getting after substitutions Cs from this. Okay. So, now we have equation 9. So, now if we do plot, equation 9 is this, in the left hand side is this, Ct0 is the initial tracer concentrations that is known, and Ct, that is the tracer concentrations if we conduct any tracer test, that we can get tracer experiment. Ct will get at different time. So, at t is known, Ct is known at that particular time. Ct initial it is given, Ct0 is given. Okay. Tau is also given. So, alpha beta, that is the two unknown parameters that we have to find out. So, that is why we are doing treasure test. And now, in this equation, this is left hand side and right hand side t by tau is there. So, here's left hand side ln Ct0 by Ct0 minus Ct will plot here y axis and x axis time will plot. So, then these lines we can get, means what are the value, means numerical value means tau and Ct0, Ct, t, these are the things are given. So, this plot or graphs we can get. So, this is the intercept and this is the slope. So, from the slope, slope equals to this component is the slope and this is the intercept. So, intercept is this and slope is this. Okay. So, from equation 9, if we do plot y axis this and x axis this time. So, thence we will get slope and intercept. So, slope and intercept has some numerical value. So, this value we can put. So, thence from this slope and intercept we can find out alpha and beta value. So, with the help of treasure test, so we can find out alpha and beta value. So, once we know alpha and beta value, then the volume, system volume, so actual volume taking part or participate in the reaction. So, we have reactor volume, let us say this, but actual systems volumes that is used or utilized for the reactions is this. So, rest means Vs minus V, that would be the dead volume. Okay. So, the volume does not take part in the reactions or the system. So, this. Okay. So, now similarly in case of the beta also, we have volumetric flow rate is this, that way we are passing the streams through the reactors, but actually that Vb, that is the volumetric flow rate bypassing, means channeling is there. So, or bypassing is there, that volumetric flow rate. So, actuals, let us say this is 10, but from the system it is bypassing, let us say 0.1. So, V systems equals to V naught minus V B. So, it means V s equals to 10 minus 0.1. So, 9.9 and dmq per second or whatever the unit. So, let us say this. So, system volumes would be little bit lower than the actual volumetric flow rates. Okay. So, this way alpha and beta parameters we can find out using treasure test. So, we have to find out alpha beta by considering treasure test. So, once we know that alpha beta value, then we can use that equations we have developed for the reactions. So, these equations we have developed, this equation 4 we have developed. Okay. So, now in these equations alpha value and beta value have to substitute, then Ca the concentrations when reactions is there. So, we can find out the exit concentrations or effluent concentration of the reactions. Okay. Okay. Did you get my point or not? So, it is this way actually, means using the treasure test you have to find out the parameters, parameter 1 alpha, parameter 2 beta, and before doing the treasure test we have done the reactions. This is the reaction test, reactions, and we are going to find out C and X, and these model systems we have developed by considering so many steps we developed. This is the equations, effluent concentration. So, equation 4 is useful and equations 9 is useful. So, equation 9 from the treasure test that was developed and equation 4 that was developed for that particular reactions. So, from the treasure test now equation 9 and 4 both simultaneously we have to use, and then alpha beta parameters if you know that we have to put there, that way you can find out exit concentrations and conversions. Now, we will go for a numerical example. Okay. So, if we solve a numerical examples, then the theory of these two parameter models means that would be much more clear for you. So, now let us go for numerical example. C states with dead space or dead volumes and bypass systems is there in our real system. So, if we let us see a second order reactions we are considering conducting in these reactors. Okay. This is model system. So, let us say we have a C star reactors, this is a C star reactors. So, maybe there is some dead volume is there, bypass may be there. So, if we conduct this reactions here, so means this is then, so what would be the conversions or exit concentrations? Initial concentrations of Ca Cb0 is given, let us say. So, by considering or doing these models, how we can predict. Okay. So, that would be our job. So, how the conversions we can expect without conducting the reactions by doing this model. So, this treasure test, by considering these models we have already done, already have discussed the model equations we have developed. Okay. And here for this particular reactions, so initial treasure concentration is given at 2000 milligram per dmq is given, and treasure test was conducted for this particular system. So, here Ct and T means treasure concentration, that is the Ct milligram per dmq and the times. So, I said when these model systems we have to before means we are not going to do the conduct the reactions, only treasure test we are going to do, and from the treasure test we can get treasure concentrations at different time. So, let us say time 4, 8, 10, 14, 16, 18 at this particular minutes. So, we are collecting that treasure from here at different time intervals. So, this treasure concentrations we are measuring and we are getting exit treasure concentration is like this. Okay. And there other things or parameter is given, system volume or reactor volume is 1 meter cube, volumetric flow rate is given, reactions rate constant is given for this particular reactions rate constant is given, and total feed rate is 2 kilomole per meter cube, and equimolar feed is theirs, A and B both are theirs. So, feed rate is 2 kilomole per meter cube is given, volumetric flow rate is given. Okay. So, now we have to start solving this. So, now from the treasure test equation 9 we have model we have developed. So, here treasures this Ct and T is given. So, once and Ct0 is known, Ct0 is known, that is given, Ct known is 0 is 2000. So, then Ct0 is known. So, this Ct0 by Ct0 minus Ct we can find out from this value, and Ct0 equals to 2000. So, we can find out this we can develop this table. So, once this developed table is this. So, then after that, so ln Ct0 by Ct0 minus Ct we can find out in the left hand side. So, in this equations we need this. So, now we have to plot Ct0 against T. So, Ct0 against T, if we do plots in ln's, this is ln Ct0 by Ct0 minus Ct against T if we plot. So, then based on these tables we can draw this line, and see here this is the intercept value is 1.25 and slope equals to 0.115 minute inverse. So, we are getting slope and intercept. Okay. So, slope and intercept equals to 1 upon and 1 minus beta, that equals to intercept equals to this, from there beta equals to 0.2 we can get, and intercept is this, oh sorry, this is the slope, oh this is intercept and this is the slope equals to this is equals to this. So, this value we can put it here. Beta value we have calculated, we can substitute here. Tau value we know, tau equals to space time volume by volumetric flow rate, that is given. So, 10 minutes, and we can substitute this tau here. So, then we can get alpha value. So, alpha equal to 0.7 and beta equals to 0.2. So, using treasure test on from this experimental data whatever given, and using these equations means model equation that was developed, we can find out alpha beta value, that would be the useful for our reaction system. So, this is only treasure test data was evaluated, and now means similarly if we conduct the reactions. So, these reactions now we are conducting. So, here instead of treasures we are passing, so only reactants, here it was passed treasure, and now we are passing reactants A. So, reactant ray also will follow the similar path. So, few streams, a stream will pass through reactors, another one will pass through bypass. Okay. So, now material balance for system, if you do input minus output plus generations equals to accumulations. So, at steady state there is no accumulations. So, since there is reactions A plus B going to C plus D, so reactions is going on there. So, it has a particular rate RAS equals to minus K something CA square it is given, or if it is given, or otherwise rate law we can consider this. Okay. So, input equals to Vs into Ca naught, this is the Vs into Ca naught, and output equals to Vs into Cas. Rate of generations equals to rate of reactions minus RAS into Vs, accumulation is 0. So, then this is the material balance, and then rate law equals to this we can say, or we can, if equivalent feed was there. So, rate law we can write this way, minus R is equals to K into C square. So, now we are substituting this here. So, then after substitutions we can get equation 3. So, equation 3 we have developed. So, now rearranging equations, this equation 3 we are rearranging and simplifying. So, once we rearrange these equations and simplifying, and after that we can get Cas equals to minus 1 plus square root of 1 plus 4 tau s k into Ca naught by 2 tau s into k. So, equation 5 we can develop. Okay. So, from equation 3 we can, equation 5 we can develop. So, now step 3, that is the doing the balance at junction 3. Here we are doing the material balance, input equals to output, this is the input line, this is input line, this is output line. So, input equals to output. So, if we rearrange this, so then we can get this, okay, Ca in terms of Cas and Ca naught. So, now Cas equation 5, from equation 5 Cas we can get, Cas we can substitute is also here, then in terms of Ca we can get, or else Cas directly we can find out by measuring tau s and k value. So, now here if tau s k is given, small k value is given, and tau s equals to Ca naught is given, Ca naught equals to 2 kilomole per meter cube, that is given, we can put it here, and tau s equals to 8.7. So, from alpha beta value that we have developed in earlier cases, here alpha and beta value 0.7 and 0.2 that we developed. So, the now these equations we are expressing in terms of alpha beta, or alpha beta we can substitute here, beta equals to this and alpha equals to this, and so once we know that, so then if we Cs we can Vs, that is this we can guess, tau s we can get, small Vs equals to this. So, this we can get. So, number 1 small Vs, capital Vs, if we know, then tau s we can find out. Okay. So, here alpha beta from the tracer test we found, and that we are using this here, beta and V naught is known, V naught equals to 0.1 meter cube per minute is given, V naught, capital V is given, V by V naught or V by V naught. So, then alpha into tau into V naught value is given. So, tau is equals to 10 minutes, alpha equals to 0.7 it is given, and then Vs system volume we can find out, tau s equals to Vs by Vs, that is equals to 8.7. So, actual space time tau equals to this, but this is system space time is this. So, this is less than this due to the bypassing. Okay. So, now we can find out Cas from these equations. If we put tau s value, k value, Ca naught value, so the Cs value we can find out, and solving these equations means these equations. If we solve here V naught Vs, if we substitute Ca naught, substitute Cas also we have obtained and we can substitute here, Ca we can find out. Once we know Ca, then conversions we can predict, that would be 51% let us say. Okay. So, Ca naught is given, Ca we have find out, and then conversions we can predict, that would be 50%, 0.51, that is approximate 51%. So, if we do not do any tracer test, so then if real reactors that we have developed fabricated, that we in that reactors if we conduct the reactions, and if we want to find out what would be the conversions if we conduct the same reactions. So, in real reactors the concentrations we have this type of equations we have developed long day backs first few 3 or 4 class in the lectures you can see there. So, we have discussed this type of equations second order reactions, as I think this type of equations we have developed. So, here if we substitute tau k C A naught, this is tau and this is k. So, then actual concentration is this and conversions we can get 66%. So, real CSTR whatever, this is the CSTRs where bypass we are not considering. So, means this is the ideal CSTR. So, in this case conversions is 66%, but when in our real systems if there is a bypass is there, so then conversions would be slightly lower. So, here slightly lower, here bypass stream was there. In this reactor bypass stream was there. So, this is our ideal reactors, but here bypass stream is also there. So, the model system. So, therefore, in the real CSTRs with bypass or dead volume is there, then conversions always would be lower than the real systems. Real system CSTR would be always lower than ideal CSTR system to the conversions. Okay. So, thank you. So, today is up to this, I think it is clear to you. Okay. So, 2 parameter model is over. So, by considering again I am just repeating. So, means what we have done actually. So, 2 parameter models we have developed due to the reactors having channeling and bypass. So, we have considered the volume is like this and volumetric flow rate is this, and then we have considered this is the real system, this is the model systems. So, if we conduct these reactions, how we can find out exit concentrations or conversions, that how we can find out. So, for that we have developed, means for this particular model systems we have developed equations in terms of alpha beta. Okay. So, in terms of alpha beta this equation 4 we have developed for considering the reactions. Okay. Similarly, once we do the tracer test in the same reactors in the model systems, so there also we have done the material balance in the systems and at the junctions, and by that way we have developed some equations. So, that equations may be equation 9s we have developed. So, from the tracer test in our model systems we have developed these equations, and from the reactions we have developed equation 4. So, these equation 4 and 9s are useful to find out the actual conversions. So, now in the tracer test the equation 9 that we have developed. So, now we are plotting this by from the tracer experiments we can find out alpha and beta value. That alpha beta would be useful for to solve equation 4, alpha value is required, alpha and beta value. So, then therefore, we have considered a numerical problem. So, there's bypass and dead volume is there, and for that systems tracer experiment results are given, that we have done by plotting these plots, and then we have find out alpha beta value from the tracer test. Then for actual experiments material balance we have done, and there we have substituted those alpha and beta value and we find out conversions. So, or concentrations, exit concentration or effluent concentration, that way we can find out the what would be, or we can predict what would be the conversions, okay, for our system. Okay, thank you. So, today is up to this. So, RTD or RTD residence time distribution function on non ideal reactor, that part is over I think. So, okay, thank you.